Good afternoon, and it's good to be back. Since we last talked about estimation, you've had a weekend, you've done some homework, and you've taken an exam. But let's get our thinking back to estimation and recall that when we last talked, we said, what's the average hat size for males in the population? So that was a question about a population, meaning that we're looking for a parameter, and what we want to estimate is mu, the population parameter. Now, how would we do that? You would not have to be overly intuitive to think that X bar is probably a pretty good estimate. Now, X bar would be the sample average, so you'd take a sample of some size n, and you'd calculate X bar, and you would tell me that X bar is going to be approximately equal to the population parameter, and I would agree with you. And in fact, the central limit theorem tells us that the average value of X bar is in fact mu. So on average, we'd be correct if we said that X bar was about mu. The problem is we don't know how close that average is. We know it's close, but we don't have quantitative parameters on how close. So better than just a point estimate, X bar, it would be better to have a 1 minus alpha confidence interval estimate of the parameter mu. So what is that? Well, that would be an interval, you know, just like always, it's a little subset of the real number line, and it's got a left-hand endpoint and a right-hand endpoint. So a confidence interval estimate would be an interval, but we would think that mu would be in this interval between L and R. And we would think that 1 minus alpha, if it's a 1 minus alpha confidence interval, 1 minus alpha is the confidence. That would be equal to the confidence, which is to say the probability that L is less than mu is less than R. So what do we have to do in order to build such a confidence interval estimate of mu? Well, we just set 1 minus alpha. We say, well, I would like to have a 95% confidence in the estimate that we are going to build. 95% confidence. That means 1 minus alpha is equal to 0.95. By the by, of course, that means that alpha would be equal to 0.05, and if we cared, and of course it will turn out that we do, half of alpha, or alpha by 2, would be 0.025. Now we'll see why that's important in just a second. So coming back to what we're after here, a left-hand and a right-hand endpoint, so that the probability that mu is between those two is equal to 1 minus alpha. Well, we're going to have to do some algebraic manipulation, and I'm going to try to skip most of that because I don't think that's primarily what you're interested in. But I think if you use a little imagination, you can see that by doing algebraic operations, that is adding things and subtracting things, I can get from an inequality L less than mu less than R. By doing algebra, I can get to an expression L minus X bar is less than mu minus X bar is less than R minus X bar. What have I done here? Well, I've just subtracted the same thing from each term of that inequality, and we know from a college algebra course that we've taken that that's perfectly permissible. Now, another thing I can do is to divide each member of this inequality by a positive quantity. If I divide by a positive quantity, I will not change the sense of the inequality, and the sense is L less than mu. That's the less than is the sense of that inequality. Mu less than R, the sense here is that mu is less than R. So if I divide by a positive value, I maintain the sense of the inequality. And so let's divide by the population standard deviation divided by the square root of the sample size. Now, why did I pick that? Because the central limit theorem tells me that x bar has this for its standard deviation. Now, if I do that for this term, I've got to do it for all the other terms as well. Minus x bar over sigma over root n less than r minus x bar over sigma over root n. Now we've made some real progress here. I'm going to scroll up a little bit. You see that what we've got right here is almost a z, isn't it? Z is x bar minus mu over sigma over the root n. So this has got the sign of the numerator wrong, but if we could make this x bar minus mu in the numerator, then we'd have a z right here. Well, we can do that. We just have to multiply through by -1. However, if I multiply through by a negative quantity, I will have to reverse the sense of these inequality symbols. So let me multiply through by -1, and be aware when I multiply through by -1, I'd have minus mu plus x bar, which I'm going to write as x bar minus mu. So I'm going to use that same technique as I go through here. This becomes a minus L because I multiplied by -1. Sigma over the square root of n. Now I got to reverse the sense of the inequality, and this becomes x bar minus mu over sigma over the square root of n, and I've got to reverse this, and this becomes x bar minus r over sigma over the square root of n. Okay, so that's all correct. We're used to seeing these inequalities as a less than, but you know, if I read this from the right-hand side to the left, I've got this quantity less than this quantity less than this quantity. Let's just write it in that way. And let's just write, if you'll give me just a second, x bar minus r over sigma square root n less than x bar minus mu sigma over root n less than x bar minus L over sigma over root n. Wow, we've done a lot in a short period of time here, but you see what we've got is equivalent to what we started with clear up here. We've done algebraic maneuvers. They're all correct algebraic maneuvers, and so we wanted L and R to be selected so that the probability of mu being between these two was 1 minus alpha. The probability of mu being between these two is the same as the probability of x bar minus mu sigma over root n being between these two things, and so that's equal to 1 minus alpha. Now that seems too easy, and I'm afraid it is, because think about what we're doing here. We're trying to get an estimate for mu, and so we're walking up to a population of hat sizes. We don't know mu. Why would we know sigma? If we don't know mu, we probably don't know sigma either. So we don't know either of these. Now this is the thing we're trying to estimate, so it's okay if it appears in the numerator, and I would get a value to plug in for x bar by taking a sample of size n. That gives me a value to plug in for n, but I don't have a value to plug in for sigma. However, I would have an estimate of sigma. I could use the sample standard deviation to estimate sigma. If I do that, this is no longer a z. Let me write that down. P x bar minus r over s root n less than x bar minus mu over s root n less than x bar minus L over S root n. So we were so close to having exactly what we needed, a right hand and a left hand endpoint for this confidence interval, but now we've pushed back a little bit, because instead of having a z here in the middle, if I know the distribution, I can calculate any probability. I've told you that a lot of times, and some of you even believe it. But now I've got not a z anymore, but an x bar minus mu over s over the root n. Well, all is not lost, because I know that distribution too. It's not a z, but it's a distribution that we know, and the distribution is students T distribution. Now, student was a pseudonym or a pen name of William Gossett. And William Gossett was a brewer and a statistician, an experimenter working for the Guinness Brewing Company in Dublin, Ireland. I want you to look up William Gossett in Wikipedia, and you'll get a nice photograph of William Gossett and the names of his 4 children. Actually, I think it's 3 children. His wife and 3 children, his birth date, and the date of his death. And you'll learn more about William Gossett. But we're going to, in the next video, we're going to talk about students' T distribution, because knowing something about students' T, which is quite easy, is the whole key to calculating a 1 minus alpha confidence interval. So I'll see you then in the next video.